All right, so for today we're going to talk about using graphical methods to solve small systems. And so by small systems, I'm referring to two unknowns in our systems. You can extend that to three unknowns, but it just gets cumbersome. With two unknowns, we're at least looking for where lines intersect. With three unknowns, it would be where three planes are intersecting. So we're not going to extend it that far. But then what that does is it sets us up for a really important topic in when solving these linear systems as to what a well-conditioned or an ill-conditioned system is. So let's jump into that graphical method, okay? So what I want to do is let's take this system that's 3x1 plus 2x sub 2 is equal to 18, and then negative x sub 1 plus 2x sub 2 is equal to 2. All right, so to solve this graphically, we would want to plot this on an x1 versus x2, and then just find the point at which they intersect. Okay, so to do that, we have x2 is a function of x1, and so we're going to rewrite the equations into these two functions. So equation 1 becomes x2 is equal to negative 3 halves x1 plus 9. And then equation 2, we get x2 is equal to, of course, we're doing the same thing to both sides. Add x1 to both sides, then divide by 2. So x2 is 1/2 x1 plus 1. And so open up your MATLAB and let's go plot those. And so to open up a new script, and let's just save it as something. So class examples. And so for this, let's do the clear all, close all. And then for this first system, we need to define our domain for x1. And so I want you to use a domain from 0 to 6. So linspace 0, 6, put 100 points in there. And so this will be our x1. And then we're defining our two different x2 equations, okay? So recall we've got x2 is equal to this and x2 is equal to this. So two different linearly independent equations. And then, so x2 equation 1, do EQ1 is equal to, and so this is negative 3 halves times x1 plus 9. And then our second equation, so x2 equation 2 is equal to 1/2, so times x1, then plus 1. All right, so let's create a figure and let's plot these. So x1 with x2, that's coming from equation 1. We're going to hold on and then plot x1 and then x2 is coming from equation 2. All right. So we do need to spruce this up a little bit. And so in order to do this, let's make one of them blue, one of them red. So we'll make the first one blue. Let's do a line width of, let's say, 2. Do the second one, make it red. Single quotes here to make these strings. Okay. Put that grid on. Let's put some labels on here. So X label, let's do This is our x1 variable, y label. Let's make that an x2 variable. And then let's put a legend on here so we know which one's which. Well, while I'm at it, I'm going to increase my font so you can see this a little better. Oh, I guess we're already there. So we're at 18. And so, so for our first equation, is this guy. Our second equation is this guy. So we can say x2 underscore 2 is equal to this. All right. So let's see what happens when we run this. Ah, there we go. Excellent. So in this equation, or these two different equations that we've now put into our system, and I'll give you a minute just to catch up here. There we go. And so with this, we're now looking at our first equation, which is a single line. It has a linear slope. And then our second equation, right, both as a function of x1. And then to find where the solution is in this nice and simple system, we would just zoom in. And so this is deliberately an equation where our point of intersection is x1 is equal to 4, and then x2 is equal to 3. And so we can then solve these equations, or at least go back to our original equation, which is 3x1 plus 2x2 is equal to 18. We can insert this, those values into our equation, and we can see that if x1 is equal to 4 and x2 is equal to 3, that 3 times 4 plus 2 times 3 is equal to 18, and then negative 4 plus 2 times 3 is going to be equal to 2. Okay, so we can solve that, and we've done that before, where we've taken our graphical guess and then put that back into our equation to see if that's correct. We did that with our roots. And so in a situation where you don't have these nice integer answers, you would then, as we've done before, you're going to zoom in and zoom in as far as you can until you get the right precision that you're comfortable with in the graphical, the right precision that you're comfortable with these solutions. Okay. All right. So so this is just a nice feature of linear systems, and a nice feature of what we're calling small linear systems. Okay, so that's if we have two unknowns. So what I want you to do is take this template essentially, that we just worked through, where you have a domain, you're defining your two equations, okay, which are x2 as a function of x1, and then creating a figure. And I'm going to give you 3 of these problems and work through this and plot each of these. I'd like for you to find a pencil. Take about 10 minutes and plot these 3 systems. So system 1 is going to be negative 1/2 x1 plus x2 is equal to 1. And we'll call that equation 3. Equation 4 is negative 1/2 x1 plus x2 is equal to 1/2. System 2 is negative 1/2 x1 plus x2 is equal to 1. That's equation 5. And equation 6 is negative x1 plus 2x2 is equal to 2. and then system 3. Equation 7 is negative 2.3 divided by 5, x1, plus x2 is equal to 1.1. And then equation 8, negative 1/2 x1 plus x2 is equal to 1. Okay, and so what I want you to come up with, let's take about 10 minutes and then generate a figure that has 3 panels that has system 1, system 2 in it, and then system 3. All right, any questions on the instructions here? Give me a thumbs up if you're with me on what I'm asking you to do here. Okay. All right, Federico, Kyle, comfortable with this? Okay. All right, I'm going to pause the video and then we'll come back to it in 10 minutes. Okay, so at 10:25, have this plot ready to go. All right, as you're finishing this up, I'll pull my plots up. All right, so what you should be seeing now on your own plots are, here's system 1 is in the top panel, system 2 the second, and then system 3 in the third. And you had to use the subplot function to do this, so it's a 3, 1, and then here's our first panel, second panel, third panel. And so in looking at these equations, one of the things that we see here are, or that I hope you see here, are that in this first equation, we end up having the same, let me pull this up, we've got system 1, system 2, and system 3. When you solve for x2 as a function of x1, is that in the first system, we have the same slope on x1, but with different intercepts. Okay, so so we see here that we've got the same slope here with these different intercepts. And as we think about what this system is actually doing, it actually doesn't have a solution, okay? Because graphically, these lines are never going to cross. And then looking at system number 2, we have the same slope and the same intercept with these 2 equations that were given here. All right, so again, what this is saying is that not that we don't have any solution, but we have an infinite number of solutions as we work our way along these 2 lines. Okay, so those 2 lines are on top of each other. And then let's take a look at our third system. And so, we've got a slope, rather, let's look down here at the bottom. Okay, we've got a slope that's 1/2 and an intercept that's 1 for our second equation, or equation number 8. And then for equation 7, it's a slope that's close to 1/2 and then an intercept that's close to 1. Okay, so what you're seeing here are that these 2 lines have very similar slopes and very similar intercepts. Okay. So what I want you to do is to take, graphically keep these in mind, refer back to these plots as we move through our next piece. And we want to talk about the condition of a system. okay, which is telling us if we have a well-conditioned system, then its solution is going to be unique and easy to find. If we have an ill-conditioned system, then it's going to be difficult to find. You know, their solution is yeah, it's just difficult to find, or an ill-conditioned system are one that we would say has an infinite number of solutions, like in our middle system, or no solution at all, which is in our top system. Okay, so keep these equations in mind and keep those plots in view. Let's see if I can do this here by keeping these plots. Okay, move those off to the side, and let's take a look at these. So the way that we've been expressing all of our systems, our linear systems, has been such that we have a matrix A multiplied times the matrix X, and that's equal to the matrix B. All right. So, sorry about that. Right, so if we express our first system in terms of an AX is equal to B, then let's write out our A matrix. So the A matrix for our first system is going to be a negative 1/2 and a 1, and a negative 1/2 and a 1. And so and then our B matrix, let's write that out too, where we'll have a 1 and a 1/2. And so calculate really quickly the determinant of your matrix A. So the determinant of the matrix A in the first system is going to be negative 1/2 multiplied times 1. And then we're going to subtract negative 1/2 times 1. Okay, so it's the 1, 1 element multiplied times the 2, 2 element, minus the 1, 2 element times the 2, 1 element. And you can see that what we're going to get is 0. And so, so this is our essentially our tell. This is what we're going to be using to determine what our system conditioning actually is that in an A matrix, okay, if we have 0, then that here tells us that this system, you can't solve it because there is no solution. So let's look. So if that's system 1, let's look at system 2. And so here our A matrix for system 2 is equal to negative 1/2, negative 1, 1, and 2. The determinant of A is negative 1/2 times 2 minus 1 times negative 1. And then we're also going to get here a 0. So for system 2, in system 2, recall that we had an infinite number of solutions. And so for an infinite number of solutions, right, we also see that our determinant is equal to 0. All right, so you can kind of see a theme here. Anytime you've got an A matrix, you take that determinant, it's equal to 0, we're going to have problems in solving the system. All right, so now let's take a look at system number 3. Okay, remember system number 3 is one that we had similar slopes and similar intercepts. And so here in system number 3, our A matrix is equal to negative 2.3 divided by 5, negative 1/2 in the 2, 1 position, and then a 1 in a, I believe we used 1.1, I think. Oh, let me get this backwards here. 1.1 and a 1. And so the determinant of A, which it doesn't look like I calculated correctly, is going to be negative 2.3 divided by 5 multiplied times 1. And then we're going to subtract negative 1/2 multiplied times 1.1. And let's do that calculation really quickly. So 2.3 divided by 5. Or 6. And then plus 1.1 divided by 2, 0.55. And then minus, this gives us 0.09. All right, so continuing with this theme is that we are able to find a solution, okay, with our system number 3. Move this out of the way. Okay, we are able to find a solution with our system number 3. However, because these two equations are so similar to each other, you can see that the determinant itself is really small. The determinant is equal to 0.09. Okay. So these are all considered poorly conditioned or ill-conditioned systems. Okay, there is no solution for system number 1. There is an infinite number of solutions for system number 2, and then system number 3, because our the solution can be difficult to find if this is the case, particularly in larger matrices. And so we have a number that's close to 0. Okay, now how close to 0 we're comfortable with is going to be up to you and the type of system that you have. And this actually introduces an entirely new field of mathematical study, which is called sparse matrices. So if we can imagine a lot of zeros in a matrix, then it becomes difficult to invert. And this is also what the determinant of these systems is telling us, okay, is that if you can't invert the matrix, right, kind of back to what we've done before with our solution here, where we say that B, rather, X is equal to A inverse B, okay? That if you can't invert the matrix, you can't solve the system, okay? And so hopefully this is showing you something that we've kind of done before, or, you know, this is ringing some bells because we spent the last couple class periods talking about determinants and then inverting a matrix. And always we would have, when inverting the matrix, when we were using the adjoint method, okay, is that the inverse of A is the adjoint of A divided by what? The determinant of A, okay? And so if the determinant is close to 0, then that means that this inverse is going to be, if it is 0, that means we can't calculate the inverse. And if it's close to 0, it indicates that we're going to have some screwy values. We're going to have some of our inversions that aren't going to give us very good results, okay? And so let's then do this on the first system that we started with. So that first system was, what is that system? The first system is 3x1 plus 2x2 is equal to 18. And then negative x1 plus 2x2 is equal to 2. And in this system, the A matrix is equal to 3, 2, negative 1, and 2. Take the determinant of A, and we get 3 times 2 minus 2 times negative 1. And then we get 4. Minus, no, that's 8 actually. And we get 8. Okay? And so our number here, our 8, is far away from 0. Okay? Or rather, it's not close to 0. So that indicates that it's a well-conditioned system. Okay? So the principle is this, is that when setting up a linear system into our matrix form, AX is equal to B, if the determinant is close to 0, it's ill-conditioned. It may not have a unique solution. It may have too many solutions, no solution at all. Or if it's close to 0, it's going to be difficult to solve. All right? And so in your practice problems, you're going to be using the graphical method to solve multiple systems. And then also calculating the determinant for these systems. Okay, using the graphical method, plugging that back into your systems, let's just make sure that the values that you're coming up with are actually solutions. And then also look at the determinant to make an assessment on whether the system is well conditioned or not. And if it's well conditioned, finding that solution should be pretty easy to do. You should be able to find it. And so this is generalizable. Okay, everything tonight is going to be 2x2 matrices because, you know, as we're looking at this and we're doing this, it's going to be there for our small systems graphically. But this is generalizable to much larger systems. And if any type of matrix that you have has a determinant that's close to zero, it's going to be difficult to invert. And so that is called, there's a name for it, it's called a stiff system. So a stiff system has a matrix that's difficult to invert. Often you don't encounter matrix inversions. It just so happens to be that in dynamics, which I also teach, you do have to invert what are called mass matrices. And so those need to be well conditioned in order to invert them. Otherwise, that has some consequences on the properties of the dynamic system itself. So, so we'll finish with this. It's just one of the things that you find in matrix algebra and in just dealing with matrices is that you can learn a lot about an entire system that you're analyzing, whether it's a thermal system, a mechanical system, an electrical system, simply by setting this up in this AX is equal to B format, and then taking the determinant of that A matrix and that A matrix itself or whatever matrix that you have. If you can't take the determinant, then that would indicate that it's going to be difficult to do math. It's going to be difficult to do engineering on that system. Okay. And so then that's when, you know, future courses that you'll take like controls will become important, because in controls, mathematically, what you're doing is you're changing the system. You're actually changing where those coefficients are, what those coefficients are, and then making the system controllable, making the system behave how you want. Okay, so you will see this, and you'll see this in the future. And I know that you're already seeing not matrix inversions, but solving these types of systems and circuits using Cramer's rule. Okay, which is what we're going to talk about tomorrow. All right. Any questions as we wrap this up? You guys feel pretty good about it? I hope so. Excellent. So hopefully this will be a pretty light practice problem load tonight. And then tomorrow we'll talk about Cramer's rule and programming Cramer's rule. All right, y'all have a great day.